Okay, so let's get going and see if we can get out of here by 4 again. That will be rewarding ourselves for working hard. In this, I'm really going to, for this section, try and only stop at give you the essence of this, because we come back to the detail of everything, so that we don't spend a lot of time discussing this and then rediscuss it when we get to the actual topic. So the essence of this unit in here is basically, I think I can summarize it in 3 sentences, what we need to take forward. And the first point that matters is that we said that what we know about OLS is only suitable for data like that. And what do we know from that application that we did, having so many versions of the same software? We know that in that application of ours here, we know that this data, some of the series look like some of the non-stationary depictions here. Some look like random walks, etc. And when we model this export function, on each of those variables, if this is, for instance, exports and this is world income, our null is that world income doesn't matter. It has a 0 coefficient there, and if it's in logs, the elasticity is 0. That's our null that we want to prove wrong. That is different in frequentist economics. That's how we do it. If we use Bayesian econometrics, then we would put a prior there, like we think the elasticity is unity. For each 1% increase in world income, that will lead to a 1% increase in our demand. We will have some expectation, some prior, based on other studies, based on the data, whatever the case may be. But we set it like this. And that beta parameter comes from a distribution like this, based on the fact it's more difficult to think about this in a time series context. In a cross-section, it makes a lot of sense. If we analyze, say, height and length, BMI, and some health outcomes or lifestyle, or incomes and expenditures, you have people on the upper set. When you take a sample of respondents, some will be high income earners and some will be low income earners, and the average effect will be around that parameter. In time series, it's a little bit difficult to grasp that concept, but it's still, we always have above the mean and below the mean, with less and less probability, less and less frequency towards the tails. And then we know that there are certain values here in terms of standard deviation that will give us, say, a total of 5% in the tails. That will be the rejection region when we analyze this hypothesis. But this, if we just look at the beta distribution, this will be in terms of units of the variables. What is a 1 standard deviation? So that is difficult to judge. That's why we measure the standard, we calculate the standard error, which is a measure of the spread of this distribution around the beta, and that gives us our good old t-stat, which is then we know that for a standard t-distribution above these critical values of minus 1.96 and plus 1.96, we have a total of 5%. And that is the probability of making a type 1 error. You're all still good with that? Okay, so because this is crucial, because just to remind ourselves, the type 1 error is falsely rejecting the null, whereas a type 2 error is fail to reject a false null hypothesis. We should reject, but we don't. And which one is more crucial? Statisticians believe that we can equate that type 1 error as sending an innocent man to jail. That's the one. That's what we want to minimize. Some textbooks are a little bit more brutal. They talk about hanging an innocent man. So let's soften the blow a little bit and not try to send innocent people to jail. Versus rather, keep that probability as small as possible. It will always be a trade-off. The two distributions overlap. This also comes back into play when we talk about unitary tests, the power versus the size. It's always a trade-off, where power is a function of type 2, and the type 1 error is then the size. Type 1 error size, probability is 1 times the type minus the type 2 error. But all of this now seems like you think I've lost my marbles now. Why do I now go back to statistics, first week statistics? It's because when our data looks like everything but that series, then that it only works for this series. We will get to the fat tail story just now. We will get there. We already mentioned that economic time series have these trends. Either you can see this series is not autoregressive in nature. There's no AR component there. It's simply a function of time. This one has an AR component with a parameter of 1. So that is a specific process, a random walk, and we can add a drift. And we can even add a deterministic component in there if we want. So the idea is that when we're going to analyze data, we're going to be presented by something like this orange line. And then we have to use knowledge that we have to deduct something about that series. So a lot of this will repeat itself, so maybe I can skip this. This will also pop up in the next section. But you can see that this, and we can actually demonstrate this. This is simply writing a small program, and this was not done in R, this was done in the EVIS programming language, where we start with the seed value, and then we generate y as a function of the previous period plus some random number. And we can see that it is literally possible, if you generate this 100 times, that you will get 100 different trends, trending upwards, trending downwards, trending up and down. It's totally unexpected. But this is what we typically see when we see economic time series. If we have a random walk with drift, typically it will follow a straight line almost and hardly ever come back to that. It will only occasionally cross that trend line. I just want to see where is that non-standard. Are we getting there? Oh, it's coming. I thought I missed it. So I just want to give you like the essence of what we see here. That distribution, looking at that beta distribution, that is there because the first thing that we want to take away from this, and we will get to that, is that that distribution that's supposed to look like this in the case of a stationary variable with a constant mean and a constant variance. And this gives us our probability to falsely reject the null. Reject the null when we shouldn't reject, the type 1 error. So, and we know that that values are, we can say, roughly 2. This all changes when the series have trends. To the extent, some of the papers show that if you still want to rely on only a 5% level of significance, just in 5% of the cases we will send that poor man to jail. That t-stat must be much larger. We're then looking at something around 11. Because these distributions are not this nice bell-shaped form. They start getting these fat tails. So that if you look at the same, you can see that little area and this area. And also the t-distribution. If you look at the 1.96, that area will be much larger than the 0.025 or the 2.5%. So that is the first thing. So what that implies is that if we look at a result like this, these standard errors and t-stats are not what they appear to be. The distributions are different, invalid. So that's why we said at this point we're more concerned about the values of the coefficients than about what the R-squared, what the standard errors, what the t-stats are. So that is the first thing to take away from this. And these are all the people that help us, all the scholars that help us to understand that. I think this was kind of full circle to understand the implications of non-stationary data. And if you go to the Nobel Prize page, when Robert Engen and Clive Granger received the Nobel Prize in 2003, it will say for their contribution in helping understand the impact of non-stationarity in data analysis. There are like a few highlights over time that helped us to understand things increasingly better. I think this will not pop up in in many reports on this. That was a statistician way back 100 years ago. He just played around with cards, and one's perception is kind of, if you look at these magicians that play with cards, they sort it very skillfully. And the idea is that each time you draw a card from that pack, that it's completely random and independent of the next draw. You cannot say, I'm now going to draw a 1 of hearts and then an ace of spades or whatever. Each card comes out randomly. So he drew sequences of cards and then order it, and sometimes it would have resembled a stationary process, and sometimes there would be kind of a trend. But we still agree that every draw is independent. So if you draw 20 cards and then 20 different cards, and you take that as generated data, and you regress this numbers on these numbers, should they have anything? Should this one be a causal, or the correlation between them should be very low. And then he actually find that in many more cases than expected, it shows, especially notably when the numbers formed a trending pattern, it shows up as a positive correlation. So Granger and Newbold, they were a little bit more statistical. They generated these time series like this. They literally generated if we call this Y and this X, they generated many of those combinations, 100 or so. And each time then they then regressed. They said, okay, the first one will be the dependent and the second one the independent, and they run a regression. And does that series and this series has anything in common, except for both starting at 0? It's independently generated. There's a random generator there. So actually, in none instances should there be anything going on, thinking that that and that series have something in common. And then in only 23 cases, they failed to reject the null, and all the rest, so almost 3/4, they found a supposed correlation, which is like a false correlation. That's spurious result. So that's the second important point. Phillips normalized it a little bit better. This is Peter Phillips from Yale, but he's actually an Aussie. He was the one that suggested that t-stat should actually be 11, not 2. If you want to have only a 5% chance of a type 1 error, of sending the defendant to jail that's innocent. And then these guys here, they started verbalizing the terminology. things like order of integration, being co-integrated. And here towards the end, Granger also then relied on Sagan coined the term error correction model. So, and then basically Granger joined forces with Engel, who was at this stage a specialist in high frequency volatility data, and they came up with this idea. And the first thing that we learn from this whole section is non-standard distributions with non-stationary data. And the second thing is that all of this led up to a point that we are going to address that non-standard distributions, and what are the two economic concepts that we're going to use to address that. Steady state equilibrium, because we believe that's what we learn in the macro class, that systems behave according to this steady state equilibrium, but also we know that most often systems are in disequilibrium. So even back to Adam Smith, he talked about the invisible hand bringing systems back to equilibrium. And that modeling, the invisible hand, we do by using dynamics and model that adjustment back. And that's the essence of this whole set of notes. The detail is the technicalities of what's in these papers. And some of them I think I've uploaded there, but it's the references, I believe, is in the back. All the reference will be, in any case, in the main reference of this, that paper that's referenced in the beginning. So now we're not going to talk through every little detail here, so I'm just going to scroll through. This is maybe worth a 20-second stop. At the time, this, I believe, you can see it is 2 years ago when I set up this set of notes, and I came across this graph on the dailyinvestor.com. And what do we see here? The blue line is the exchange rate, and the orange line is load shedding stages at that stage. And if they use like a moving averages of all of those stages, the more load shedding we had, the weaker the currency. So here was some improvement, and then more load shedding again, and weaker currency. Is that? Do those things have anything in common? Or can we say that all that load shedding weakened our currency? I see this and this.
So it would not make sense that if there's a lot of load shedding, productivity goes down, so even the demand for exports would also go down, therefore decreasing the demand for our currency.
Yeah, that's 100% true. And many other arguments can be true simultaneously. If the outside world look at us and say, you can't even keep your lights on, how should we trust buying your bonds? How should we build a factory there? Because how will we produce if we can't keep the lights on? So that only that sentiment factor already plays a role. But claiming there's a direct causal relationship, that's probably, I think this is what in econometrics we talk about a spurious correlation. Because it may be that there's so many confounding factors, maybe driving both, or it's this intermediate effects, this transmission effects, whether it's going through production to exports and the other branches of the real economy, or is it sentiment, what is it? So this is what we deal with. That's also why it's so important. If you run Y and X and you see a good T, the next step is not to claim victory and say, I have solved the problem. It's much more complicated like that. Sometimes what we pick up is correlation, but not causation, or at least not directly. So we have to be careful with our wording and where we go with a result like that. So now just, this is now not really Jules's application, but I'm just showing here that a little bit, introducing a little bit of the terminology that we're going to see again. So if we see a stationary variable and one that has a linear trend like this, if we difference a trend like this, we get, because if you go right 1 unit and up 1 unit, then the right units will be equal, but the vertical changes will be. And one that's exponential, if we difference it once, it will start looking like this, and difference a second time, we will have that. But this is maybe not a fit, the good fit to place this, but what Jules found was that he found more often than not, when the card numbers were increasing, that it appears to be correlated, just like this appears to be correlated, but not causal. So, first thing. Then secondly, Granger and Newbold in 74, you can see they use time series tools to generate, this is a random error term, so they generated 2 independent random walks, and then they did it 50 times. 15 or 50 observations, and they generated 100 combinations of that. But each time, this is a random walk, so it's like that orange and that blue line drifting. And then they run 100 regressions and test that they're independent of each other. They work out the t-stat, so to speak, they call it S. And then they found that the expected S value is this. It was 4.5 times underestimated actually by that factor. So instead of using a t-stat of 2, the critical value that would be right for the non-stationary data, what they did here was more than 11. So this is a table from their paper. So they only correctly reject in 13 plus 10 times, 23 times out of the 100. They correctly reject that those 2 series have nothing to do with each other. In almost 75%, in other words, of the times, it looked like there's a correlation. So that's the thing. Many time series trend like this. If we take a whole lot of series, and then we would think to not really related series just because they both trended upwards and maybe they're all a function of GDP, they look very highly related. So this is where this fat tail idea comes in. So we think the probability of getting things wrong is only that little area, but it's actually much more. And this is just what I found in a different paper with completely different application. We can see if we generate series of a stationary data and we look at this area, it will be 5%. But if it's non-stationary data, we can see the area is actually to the right of 2 is much larger. So this aligned with that Granger and Newbold that the t-stat should actually be 11. But instead of now go to our results and just use a t-stat of 11, that's not how we fix the problem. Just so long. If that is okay, and this is okay, and this is okay, can you see one solution to fix the problem? If we have consumption trending like this and income trending like that, that presents a non-standard distribution. So how can we fix the problem statistically? Differencing the data and running a regression of difference income and difference consumption. That will not that it will then have standard distributions. But why don't we do it like that? That's a quick fix. Then the problem was solved there. No. Let's just in that. Let's just stop a little bit, even if it's going ahead. If I open this consumption function. So we say if we run a regression of, if we regress the log of consumption on the log of income, just the Keynesian consumption function. If I regress that, these statistics are problematic. What is going on here? Oh, I grabbed the difference of the consumption. If I regress consumption on income, can you see that large t-stat? Way beyond. But even if we work with 11, it will be significant. So it's quite difficult. Maybe these are significant. So if we want to move to a situation where we fix the statistics, we can basically difference the series. If you think about that consumption, so that is trending. So if we difference it, can you see that that's much closer to a constant mean, constant variance process? Of course, there will always be the happenings like the COVID, but statistically, can we argue that that process has a constant mean and a constant variance? So we can difference the series, and that difference is simply consumption in period t minus consumption in t minus 1. So running the regression on the differences should fix the statistics. But what are we doing then? In this equation, I regress the different series on each other. What should we learn from? Now we can believe all the distributions will be standard, and we can believe all the stats that's going on here when running it on the differences. But what is the bigger issue for us as economists? I don't think it gets power here. Thank you. Yeah, thank you. So what is the bigger issue here? On the right-hand side, the parameter of, on the left-hand side, the parameter 0.84, that is the marginal propensity to consume. Once we difference it, what do we have then? Now it's no longer a percentage change in income that leads to a percentage change in consumption. It's a rate of change. So it's if this one changes faster, that one will change at a faster rate.
The difference means the rate of change.
Yes.
Just say that again, Prof. Just explain that coefficient.
Remember this coefficient, we interpreted it as a 1% change in YD leads to a 0.84 percentage change in consumption. So the coefficient is already a percentage change. But now the variable, now it's a change of a change, a percentage change in a change. So it's the rate of change.
Okay,
so bottom line, this is no longer that variable, that magnitude that we want to use to describe consumer behavior, spending behavior. That doesn't mean now if you get an additional 1% increase in income that you will spend 0.68% of your income on durables, non-durables, and services. So it's if that change is going in a positive direction, this is if that one, it's not even very meaningful. We don't do anything with that. It's just that we don't make the mistake by thinking that is now our marginal propensity to consume. That's why by the time we get to the error correction model, the short-run impacts will all be different, but then we don't try and go and interpret those and say, because it's no longer a percentage change, it's a percentage change in the change. So we don't go there. So this is simply saying, for us, actually, sometimes the first words I say about regression analysis, it's all about the betas. That's why you even bother. Sometimes secondary you want to forecast or do things, but firstly the structural analysis and learning what we're busy with, learning about the problem, is about what are the price elasticities of these syn goods. What are the price elasticities of our imports? What is the income elasticity of consumer demand? Because the other side of this coin is saving. Are we saving enough? Or are we just gobbling up every additional income? Is there room for saving? So these are our economic values that we are interested in. Sean, I see you still.
No, I'm just. So basically, this is just then an intermediary step.
It's not a step at all.
Okay.
That shows we shouldn't go there.
Okay.
It's an easy solution,
Yeah.
right? But we're interested in the relationship between consumption and income.
Yeah.
But now we found that this is all garbage. Not really, just not 100% correct. These distributions start getting the fat tails, they're non-standard. And in the pure time series case, it even gets skewed to the left. It's not that nice bell-shaped distribution that we believed in. Like when you're young, you believe in the tooth fairy and Father Christmas. So we believe that all those distributions are those nice bell shapes. And now we're told it's got fat tails. So one easy solution, because of the fact that, let's just look at those graphs. If we look at log of cons and log of income, if we look at those, oops, I have more in here. If we look at that, no, I'm having my finger on shift. And if I look at that, maybe look at multiple graphs. So those are the types of series that Granger, Newbold, and Phillips, and Engel and Granger showed us that the distributions will not be standard. If we difference it, these series I have generated by applying the difference operator, but you could also have written ln-cons minus 1. Or applying the difference operator in any other language. So if we look at the differences, that one and that one, and if I graph this, these look now like the type of series that OLS wants. But once we've differenced the variables, and I put this in big fat quotation marks, we difference the theory away. We cannot then say, oh, let's just difference it, but then still try and interpret that parameter as our marginal propensity to consume. So this is the second thing to remember. And now taking a step back, we are going to rely on, and it is only Engel and Granger that finally formally put all the aspects together and said, there are two things that can help us to fix this problem. We want to fix the statistics, but we don't want to lose the economic theory. So they suggested, and all the other co-integrating procedures do exactly the same, working with these concepts just in different ways, some more technical, some just different approaches. All of them will identify working on two concepts in economics. Steady state matters, equilibrium matters, but we know systems are sometimes in disequilibrium, but also dynamics matter. Your income last this year, last year, year before matters, but because maybe you saved some. So dynamics matter, equilibrium matters, those two things. And somehow, just with a clever play of techniques, we will model the long run relationship in levels, not differencing, not losing the economic theoretical parameters, but then in a second step, model that dynamic adjustment process back. In many relationships, there are fundamental drivers, and then there are things that matter occasionally. You can argue that wealth is a driving factor of your consumption, or perhaps it's just a short-run thing when you in a situation where you need to pay for medical expenses. Sometimes you need to pay for your studies. You have to go on a vacation. So you delve into your savings, maybe negatively. Maybe your saving account is actually zero, but you take a loan. So those things are not, you cannot indefinitely consume from wealth that you don't have. It's not, it's not at some point the wheels will come off. So income, your salary is basically what you can consume in a month. But occasionally you will consider wealth, sometimes you have to borrow from your own wealth or borrow from negatively from your wealth or your savings. And sometimes at a certain point, you will consider the interest rates or inflation expectations to make those decisions. So certain variables can be short-run variables. If things happen that can depress sentiment, say for instance, you lived in Ukraine and you saw the Russian tanks moving up, that's not the right time, I don't know, to do certain spendings. Maybe that causes people to, COVID caused people to just hold on to their whatever they have and not spend. Things like that, if things, anything that affects sentiment will maybe just play a role in that period that it's relevant. So that's how we're going to think about economics. What are the fundamental drivers that almost always in every single period matters? For exchange rate, the fundamentals are money balances, income differentials, and we can argue price or interest rate differentials. But then if you use some of these dynamic model averaging factor type models, you will find that certain periods, commodities matter quite a bit. Fundamentals will always contribute like 50% explaining the outcome. But then you see periods where what happened to gold or platinum is carries a weight of almost 90% of outcome in the exchange rate. So that's some of those factors. So think about an exchange rate model, and then you think commodity prices will be in the short run. It matters some periods more than being a fundamental driver. But this is also then, I think, where the science become an art. That's where you put those explanations in there. You try different hypotheses. And you will not necessarily come to the same conclusion. Yes, Marema?
What you just explained changes thinking.
Is that good or bad?
I've seen quite a number of papers. I don't know if it's wrong, but I've seen quite a number of papers which follows testing unit road. They find that is not stationary.
Mm-hmm.
They difference, after differencing, they then go to integration. From integration, they do error correction.
They difference and then they do co-integration. Oh no.
Yeah.
Then typically if two things are stationary, it's like train tracks. They should co-integrate.
So basically, for integration, this is that.
Yes. I wouldn't say it's entirely wrong. You will see papers that difference and run it like that, but that will be atheoretical VAR models. That's what we see. If we test and we don't find co-integration, you will read in the literature, difference the series and run a simple VAR model or run a model, but the purpose of that would mostly be to forecast. That is no longer a structural understanding. Yeah, so it's not as simple. It looks like now it's simple, but there's a whole lot of nuances. But difference, to take on some, it's as if you tell me that typically what we want to do is, on this consumption, we want to take consumption and income. Those two variables we want to open as a group and we want to test for co-integration. And we're going to define it a little bit more narrowly. And here the null is, just read the English, two variables, consumption and income. The null is they are not integrated. We reject that null at the 5% level. So we say that those two series co-moved, not like train tracks, but almost like there are so many different ways that we can imagine that. There's a paper written, the title of the paper is The Drunk and Her Dog. Have you seen that paper? And now, I don't know why it should be a her now suddenly. These two old ladies sitting at the bar, one has a dog, and they wander home afterwards. And a dog wanders by nature. A drunk person by nature doesn't walk in a straight line. So, but as long as the lady manages to hold onto the leash, they will stay within certain bounds and arrive home together. Maybe she must tie the leash here. I'm currently watching Breaking Bad. I don't know if you've seen that movie. It's a little bit hectic, but yeah, make me think of substance abuse. So that's one. A nicer analogy to use is two people doing a nice tango. Have you seen that, how eloquently that sometimes are done? They don't stick together like this. They move further away and closer, and it's beautiful. But they co-integrate. And the lady and the dog. So the idea is that. But then those papers that you refer to, Marema, would difference the data and test this and look at that and say, first difference and then test for co-integration, that is something, of course we will have, wow, you know, it's co-integrated, but it should be. If two series with zero means, they should co-integrate strictly. Otherwise, I don't know, maybe one of them are not so really stationary. But differencing and then carry on with analysis, that is indeed done. But only if it's not for structural analysis, if it's mainly for forecasting and impulse responses, that is done. But then there's no structural parameters to base policy upon. Maybe the impulse responses will also inform policy, so that's still good. Yeah, so thank you for that point. It's more nuanced than this. But now the VARs also have bootstrap p-values, so you see increasingly papers using VAR models in levels. So that is also possible. We should only break at 3. Yes, okay. I think, so those are the, and how we do it, there's a peep here, there's the Nobel coin, but it's a lot of money, eh? It's $1 million Swiss franc that they share. So we're coming back to this, so we don't need to look at this now in detail. But there's the 2 dancers, or the lady and the dog. It's not train tracks. It's more like bicycle tracks on a dirt road. Off-roading. So I think all of this we'll get back to. But this is now saying 2 things. Long run matters. Equilibrium matters. We will be in positions of disequilibrium. But dynamics also matter. And how that little recipe there, 1 million francs. Swiss. Huh?
221 million, just a minute.
Oh, yeah. Oh, my goodness. Yeah, that's a handsome amount. And then, if you have that coin, they invite you to go and speak at places.
Sorry, on the correction, 22 million.
And yes, that math, your little brothers and sisters can do that. But quite ingenious in terms of bringing together these economic concepts of equilibrium, steady state, and short-run adjustment. Long-run equilibrium, steady state. And when we are in a position of disequilibrium, we can adjust back and look at this. There's our marginal propensity to consume. This is the long run. But we know we want to work in stationary variables. So differencing consumption is now stationary. We will test that. All these are stationary. And if we have 2 variables that co-move, that difference between them is a stationary difference. So regress y on x, take the residual, and this is now representing all the information because the residual is equal to the actual minus the fitted. And this is now using this concept. Engel and Granger does it this way. Pesseran, Shin, and Smith basically do the same thing. They start by doing it all in one step. Then they use the bound testing approach to test for co-integration here, and you also get a very similar result. The multivariate co-integration do exactly the same thing, all in one step, but looking for more than one co-integrating vector, independent vectors, and ending up basically giving very similar results. In that export folder, you will see there's a file called co-integration 3 ways. And if you finally look at the different approaches, it's almost like if you drive to work using Waze, there's typically 3 or 4 routes, and some mornings it will take me one route, some mornings it's congested, so I will take another route. But ultimately, the results will be very similar. And just to give you that peek a little bit ahead, if you look at this document, co-integration 3 ways, I go back to the older export example, and then I apply co-integration 3 different ways, but the summary in the end is basically, in this example, it only goes up to 2013. The income elasticity, where the first column is Engel-Granger, the multivariate Johansen approach, and the Pesseran et al., the ARDL and bounds testing approach, you can see it will never give you exactly the same results, although now the software will allow us, at the point when I did this, you could not include dummies here, or you could technically include dummies, but then it will difference it in the short run. And think about what we do if we difference a dummy. You create a different animal, but we will see that, we will look at that when appropriate. So that's why these 2 models at this point don't have dummies in, but now the software allow for that. So you can say a dummy only in the long run, or only in the short run, or in both, and then it will apply it correctly. Then all of these have speed of adjustment terms, and all of these have dynamics. For these 2 methods, you have less control over what goes in, so we will see many of these are not statistically significant, but in the Engel-Granger, we have control over putting them in. So this, as I said, Google Maps, Waze, different ways to the same destination. I think in applied work, in published work, this method will receive most citations. In climate, energy, agricultural studies, I've seen this used, the ARDL and bounds testing approach, quite a bit. The Johansen approach didn't really get the use because you have to place those theoretical restrictions, like in a structural VAR, and it's not always easy. So you don't see it used so often in applied work. So that is where we want to go. Have a nice, and still, the essence of our analysis are those 2 lines for policy, for making decisions, for planning. But in order to have that as accurately as possible, we have to have all of these dynamic adjustment terms in and controls and whatever. And we can see from this, also a glance ahead, that is negative. We call it an error correction mechanism. If we are in a disequilibrium, that residual measuring the disequilibrium in the previous period, it will take a shorter time to adjust back, the higher the parameter, the closer to 1. So we will see that. And just one notification, once we estimate indifferences, the Engel-Granger will not have an R-squared that's very high, estimating indifferences. I think that one here is measuring, working it back to the one in levels. So in this work, we ultimately not chasing an R-squared. I once heard a person say, especially if you build larger models with many equations, each time you include a d log, the difference of a log, dynamics, you introduce noise. And in the ex-post period, the historical period, you may have a perfect fit. But ultimately, when you forecast with that, you have a lot of noise that you're taking into the future. It's almost better to forecast just that long-run trend going a couple of periods into the future. Are there questions? I mean, now we need to, the next step is to pave the way for the unitary testing. And that's a lecture on pure time series. That course that the students come in the 4th year and they're so terrified because they give them such a advanced course in time series undergrad that they almost feel, I don't want to do time series ever again. Did you, what is that course?
Time series for mathematics.
Yes, for the mathematical statistics students.
It's very challenging. A lot of groups it's very challenging. Because like I understand why they look at time series.
Yes. Yeah, so but when we do these things and we're going to summarize that whole course in like 30 or 40 slides, and that's all that you need to go to understand what we do with unitary testing. So we condense that and kick out all the proofs. But it's a good thing because then this is very easy. So that's now. Are there any other questions? Yes.
When you look at this concept and these, this test, so like I'm wondering whether if I'm intending to have primary, like, I think I have to use time series. I have to perform this test, or maybe I should choose, pick the one that I feel.
Yes. Yes. I think it's a good thing to be able to execute all three, right? And then if you write a paper, look at the existing literature. If it's about climate or green energy, or look at the papers in that discipline and also take from that. But it doesn't mean that you then have to use that. technically, they should all give you like the same, not exactly in numbers, but the same economic story, the same message. And then you take the one that you feel tell the story best. Yes, Kenny?
Will there be circumstances where they don't tell the same story?
Yes.
And what do you do there?
I sat with somebody from Treasury who did an exchange rate model, but higher frequency. And for some reason, I think what happened there was that when he did this parameter turned out insignificant or positive. But when we did exactly the same thing with the Engel-Granger method, it worked perfectly. So we didn't work that far to try and understand why, because it's not exactly the same, but that will be the exception. Yes, but in econometrics, anything can technically happen, but sometimes it's because we still have things wrong. Maybe there's a better variable, maybe a variable that you're missing. Yeah. Yeah, I cannot stand here and just use examples that always work. Probably the first application that you will tackle when you're back will not work at first. So, but then don't give up, you know, it's a learning process. Sometimes it's good to have to go back to the literature, go back to the roots and the basics and try and still understand better what you do. When we thought trade uncertainty and financial stress, it should be positive. There's no doubt in your expectation there that more uncertainty definitely cause more stress reactions in the financial markets. But then if you go back to the big stress event, the global financial crisis, it wasn't due to trade uncertainty. It was that whole mortgage market prime, subprime crisis that was more credit driven. And now you don't see, and the trade uncertainty was fairly low there. And that creates a negative overall relationship. And we threw many techniques at the question, but it kept giving us a negative result until we only analyzed post-financial crisis. But I could see Giovanna started to get anxious because she just wants to finish the first paper for a thesis. And now we don't get results. Yes. I am filling time now, so we have to move on to the period, and maybe discussing that is, but it's much lighter than our third year math stats. And we've seen a little bit of it already. Which one should I open now? And when we're done here, then we do the unitary tests. So this is just we're now just getting all the ingredients out, measure, so that we can bake the cake. We're getting all the everything we need. But I'm not good at that, so I can't even say what we get out. The mixer, the the measurement spoons. So let's see if we can make a little bit of progress before we have tea, and if possible, if we can be done with this by 4, that will be great to start with the unit 2 tests in the morning. So what is this about? I think for the most part, much of this is common knowledge for you. How many slides? I think it's about 40 or so. I sometimes wonder if it's a good thing to see it at the bottom here, and then it's like, okay, now we are 20 out of 40, you know. So it's a little bit of the lingo of what we're busy with, the language, the terms. We're going to define all these properties of stationarity and non-stationarity, and what is a unit root, and so forth. The best source for this is actually the 4 chapters, but not, you can see very selectively, 4 sections there, 1 section in chapter 3, couple in 4, 1 section in 5. So, but it's a very good book, that Cryer text. And is that the one that you used, Tapelu? Did you use Cryer or a different book? You got notes.
Yes.
I think it aligns quite well with this book, so maybe it's one of the sources.
Yeah, for the outcome of my textbook.
Mm.
Sure about it.
No, this one I've added, but Cryer, I say for this unit, this is the best source. Yeah, so if anything is not clear from the slides, you can definitely read more in that book. The pages, I don't think the pages are there, but it's also a substantially thick book. Yeah, so we definitely don't have to redefine a time series, but it just feels right in the beginning of a time series concepts to have an example of a time series there. And for it in economics, so much boils down to the GDP. Now, immediately, statistician hats on, and defining a stochastic process. Whoever looking at the GDP think, oh, this is a nice stochastic process. As an economist, we hardly do that. But basically, all economic time series are stochastic processes of random outcomes. And it's sometimes not so easy to think, but I mean, the GDP for 2022 was published as this. That's an actual number. What are you telling me it's a random number? Nobody spinned a wheel or roll a dice or something like that. How do we think about this in typical statistics? There's often that there's 100 balls and a few of them are red and black, and it's a random process of getting a certain outcome. How we think about this is that GDP for 2020, which was like 300 million lower than 2005. We think of it as a random outcome, but in the sense, all these things happen. So if COVID didn't happen, it could have been a different number. But now COVID did happen, so it happened to be this number. And that is that random distribution around the actual outcome. So it comes from the Greek word stokos, which means target or bull's eye. And here is that argument. So out of a large number of shots, depending on how your skill, of course, you will not hit the board at all, or maybe hit the bull's eye. But it's more that I think that's where it goes back to. But the way we think of it in an economic context, it's an outcome of so many events and shocks and exogenous things that it could have been different if few things were different. If we had more electricity, maybe we could have been by, over 6 trillion there. Or billion. So, just as we sample data to draw inferences about a population, that realization, we use the actual number that we then observe to draw then inferences about the underlying stochastic process, and we like to talk about that as a data generating process. All the things that happen that lead to that, contributed to that outcome. So in this language, the data generating process is the population, and the actual outcome or the realization is the sample. So, as economists, we can argue about what was driving that actual outcome. And that's also where we use techniques to try and understand what are if this is the outcome variable or the dependent variable, what are the things that contributed to this outcome? So this statistical approach involves matching that observed. So what we do now is that we have that observed series, that GDP. So what we do is we take 2 steps back and look at that series. And then we look at the GDP and we say, we draw on our statistical knowledge and to say that series looks mostly like a random walk. It mostly resembles a random walk with drift. It looks like an AR process, but not a random walk. The parameter is not 1. And if we can do that, because we know all the properties of these statistical processes, we can then say this series is non-stationary because it resembles a random walk, and we know that these properties, those that we prove as statistical students, we know that based on that, the series must be stationary or non-stationary. And that's basically what we do. So now we just try to understand as many statistical processes. An AR process, an MA process, a REMA, random walk with drift, AR, just a broader AR with a row smaller than 1. And this is what we will discuss next. Maybe this is a good time to break. And then go through. Already you can see this one, that alpha is not 1. And it is like this. And if we set it at 1, this is what we get. Something like that. So it's still many slides, but little information on every slide, which is good for Tuesday at 3:30. Okay, so we can take our little break so that you can chat and do email